In the previous episode titled, Why Believe in the Universe's Birth Through a Big Bang, we discussed the origins and developments of the Big Bang theory. At that time, our focus was primarily on experimental observations. However, it's important to note that the Big Bang theory isn't just a collection of fanciful assumptions based on random phenomena, contrary to what some might believe. Please bear in mind that science, not science fiction, is at play here. It's worth mentioning that even exceptional hard science fiction works are grounded in rigorous theories. The term theory in physics isn't solely reliant on experimental observations, it entails more. Regarding theoretical exploration, how did the model of the Big Bang originate? About a decade after Einstein introduced the theory of special relativity, he formally introduced general relativity. Initially, general relativity was predominantly applied to localized scenarios within space. For instance, the presence of massive objects would cause curvature in spacetime, including time itself, in that region. This was how the Schwarzschild solution for black holes was derived. However, Einstein later extended general relativity to the entire universe, publishing a significant paper titled Cosmological Considerations in the General Theory of Relativity, marking the formal birth of physical cosmology. Through Einstein's calculations and derivations, the universe model based on general relativity began to take shape. Surprisingly, the model's results were dynamic, contradicting the prevalent notion that the universe was static. Even Einstein and others found it difficult to believe these findings. Consequently, he introduced the cosmological constant into his equations to correct the model and return it to a static state. However, as we now know, observations by Hubble confirmed that the universe is indeed expanding. Thus, the inclusion of the cosmological constant became a decision Einstein regretted for his lifetime. Nevertheless, with the advent of the concept of dark energy, this constant seems to have gained renewed significance. We will delve into this topic later. In 1922, Soviet mathematician and cosmologist Alexander Friedmann, based on the cosmological principle, derived the Friedmann equations using Einstein's field equations. Friedmann discovered that the previously assumed cosmological constant could be negated, and the expansion initially discarded in Einstein's cosmological model was indeed valid. In other words, if general relativity holds true, our universe is not eternal and unchanging. It has been expanding over time. As it continuously expands, tracing back in time, there will be a moment when the entire universe was concentrated at a single point, the origin of the Big Bang singularity. You might hear people say, "You haven't seen the Big Bang firsthand, so how can you believe it?" When it comes to questions about the origin and evolution of the universe, it's indeed quite exceptional. This event occurred only once, lacking the repeatability of other scientific experiments. Even for instances without the possibility of replication, we can still study them by using similar or analogous cases. For instance, consider the evolution of galaxies. While we cannot directly observe the past and future of the Milky Way, the cosmological principle of the universe being uniform and isotropic on a large scale suggests the existence of many galaxies akin to our own. Some of these galaxies are so distant that we perceive them in their infant stages. By studying these young galaxies, we can infer the history of the Milky Way to some extent. Additionally, by observing images of merging galaxies, we can envision scenarios of the Milky Way colliding with the Andromeda Galaxy in the future. However, when it comes to the evolution of the universe itself, it's not just a matter of once, but there are also no other universes for us to observe. Therefore, our approach is to meticulously observe our own universe, collecting copious amounts of data. Subsequently, we construct theoretical models to interpret these observations, allowing us to extrapolate the past and predict the future. Among these models, the Big Bang model is one, and despite its subsequent refinements and the introduction of concepts like dark energy, it still presents many challenges. Nonetheless, it remains the most widely accepted model in the scientific community today and is thus referred to as the standard model of cosmic evolution. Speaking of the concept of time, one might ask, seconds, millennia, relative to whom? Doesn't relativity say there's no absolute time, only relative time? Indeed, as Einstein's theory of relativity was progressively validated by various phenomena, Newton's absolute concept of space and time ceased to be regarded as absolute truth. Whether in special or general relativity, velocity or gravity affects the rate of time passage, and time varies concerning different reference frames. However, when we're not studying specific scenarios but the entire universe itself, there's no reference point. We can't use another parallel universe as a reference to understand how time within the expanding universe is relative to anything. To grasp this, we need to consider how we define cosmic time. As you've mentioned, the fundamental equation describing the Big Bang, the Friedmann equation, is derived based on the cosmological principle within the framework of general relativity. The notion of time here is referred to as cosmic time. It's a theoretical construct tied to an observer moving along with the universe's expansion. It's not related to any external reference, it's relative to the universe itself. In simple terms, it can be understood as the universe's own time. This cosmic time is not the same as the absolute time of relativity. In the absolute space-time view, time, like space, is an independent entity that's uniform for all observers, regardless of their states. It applies universally, with no limitations. However, cosmic time is meaningful only when considering oneself as co-moving with the universe, typically used to describe the large-scale structure of the universe. This concept of time is severely restricted and vastly different from the concept of absolute time. In conclusion, the Big Bang theory is not solely a conjecture based on observed phenomena but is also supported by mathematical equations. Concerning the expansion of the universe and the notion of time within the Big Bang model, referred to as cosmic time, it's a construct tied to observers co-moving with the universe's expansion. There's no need for reference. It's relative to the universe itself. Hence, you can simply regard it as the universe's intrinsic time,